So we're going to continue chapter 16 talking about strong versus weak bases and then do some calculations with this. So strong for bases means exactly the same thing as strong acids. Strong bases completely break up or completely dissociate when they are in an aqueous system. So draw yourself a beaker over here. I'm dumping sodium hydroxide into it, into a beaker of water. So what you're going to see on the molecular level is mostly water in there, but then you're going to see sodium ions and hydroxide ions. And again, please note that the arrow is just pointing in one direction for strongs. So you will never find a complete molecule of NaOH in that beaker because it completely breaks out. So the concentration of the base, again, a strong base is always going to be the concentration overall of that solution. So again, if I have a 0.1 molar sodium hydroxide on that bottle, that means I have 0.1 molar of the hydroxide in there. So I could take the negative log of that, find my POH, and then I have my POH and subtract that from 14. So remember, your strong bases are from group 1A and group 2A. So again, anything from the first column, so something like KOH, something from the second column like calcium hydroxide. Again, you have 2 hydroxide in there. That's the only difference with group 2A. But those are considered to be our strong bases that you're going to need to know. So what about weak bases? Well, weak bases work the same idea or has the same idea as a weak acid. It does not completely dissociate. So what you're going to see is a equilibrium situation. So instead of a Ka, you have a Kb. So it's a base dissociation constant. So if I take our friend ammonia, NH3, and dump it into water, again, it's an equilibrium reaction. So that's why I'm highlighting it here. So I will have some ammonia molecules in there along with the water, and then tiny little ammonium ion and a tiny little hydroxide. So again, thinking of it in terms of concentration values, the smaller I draw these, the less I have in there. So with our discussion of pH, again, your pH of a strong base is going to be, approximately 13 or higher because you have a huge concentration of OH, while your pH of your weak bases are going to be maybe closer to 12 to 13, or maybe even 11 to 13 because you just don't have that much OH in there. And another idea with Ka and Kb, if you multiply these two constants, you will always get 10 to the negative 14. And that's going to come into play a little bit later on in our lectures, where you have a way to calculate a Ka from a Kb and so on and so forth. So again, same idea as Strong's, it's just we're talking about bases. So let's try a couple problems with weaks. So I'm going to start with a weak acid, more specifically acetic acid. And I'm going to give you a table of Ka and Kb values, but for these problems, I'm going to be given to you in the problem or on the worksheet or something else. So acetic acid is, again, HC2, H3O2, and I'm adding it to water. You could exclude the water if you want. I'm going to include it in a couple cases, and you're going to see why it's important to include it. But for something like acetic acid, you don't need to worry about that. So since this is an equilibrium, I could do an ice chart. You're going to see that this ice chart is going to be kind of irrelevant after we do 1 or 2 of these. So I'm starting with a concentration of 0.1 molar acetic acid. And I want to know how much of the H3O plus, I want to know my pH. So I need to figure out my H3O plus. Well, at the starting point, I have none of the ions, and I don't include water because it's a liquid. This goes down by X, this goes up by X, both of these. So the nice thing about all of these ice charts is everything is 1 to 1. So it's going to mean that the ice chart is really not all that necessary for you to do these calculations. Instead, you should try to write out what we call a Ka expression, okay? So again, Ka expression is always going to be products over reactants. You're always going to have the ions on the top and the acid on the bottom. So my ions are going to be H3O plus, or you could just put H plus, acetate ion, and then acetic acid as a complete molecule on the bottom. All right, so in terms of my equilibrium, I have concentration of H3O plus is an X. This is an X, so it's going to be X squared on the top. On the bottom is going to be the concentration of 0.1 minus X, and that's going to equal my Ka, which is 1.8 times 10 to the negative fifth. Okay, and that's a constant for acetic acid. So, like we did this back in chapter 15, this X on the bottom is going to be relatively small, okay? And I will explain how we could kind of cross this out and how we could check ourselves why we could do that. So we cross off the X on the bottom. We need the X on the top, otherwise we can't do the problem. So essentially what we're doing is taking 0.1 times 1.8 times 10 to the negative fifth. So I have X squared is equal to, I paused the video there for a second. I had the wrong number down there. So X squared is equal to 1.8 times 10 to the negative 6. So I take the square root of both sides and I get X is 1.3 times 10 to the negative third. Okay, so that's a concentration of what? Well, it's a concentration of my H3O plus, which is what I need for my pH. Okay, so once I have my H3O plus, okay, all I got to do is take the negative log of 1.3 times 10 to the negative third, and that's going to give me my pH. So 2.87. I need 2 digits after the decimal, 2 digits after the decimal, because I was given 0.10, so that is 2 digits of significance. So why can I cross out that X? Well, I'm going to show you why we could do that. So we're going to do what we call a percent ionization calculation to prove that that X can be cancelable, can be canceled, and also show you how to do a percent ionization calculation. So percent ionization is always going to be your concentration of your ions broken up over your initial concentration. So it's always going to be usually the X you solve for times it by 100. Okay, so the X you find over the initial concentration times 100. So this comes out to be 1.3 times 10 to the negative third over the initial concentration, which is 0.1 times 100, and you end up with 1.3%. All right, so the rule is called a 5% rule. So write down 5%. You could cross out the X if you are less than a 5% ionization. And that is because that X that you find is so small that if you subtracted it from the initial concentration, you would not really have a difference of concentration. Again, 1.3 times 10 to the negative third is 0.0013. Okay, so subtracting that from 0.1 makes no difference in the concentration of that acid. So I'd like to show this to you so you could see that crossing out that X is okay. Now there are times where it's not okay. Okay, so note as an acid solution becomes more and more dilute, okay, so if it gets smaller, the percent ionization increases because the water prevents the recombining of the dissociated ions. Okay, so we kind of talked about that a little bit in colligative properties. Therefore, more dilute solution, you could assume that X is small, that it could be used. So if you have a concentration less than 0.01 molarity, okay, and if your Ka or your Kb value is greater than greater than -5, so that means it breaks up a lot more significantly than typical weak acids or weak bases. So you kind of need both in order for you to kind of do X, and then you would have to do a quadratic equation in order to find that X. I'm not really going to emphasize it too much. I might show you an example or two. There's not going to be much of this on the AP test as well, but I do want to show you that there is a reason we are crossing out the X. It is, you know, mathematically an okay situation for us to do, but there are situations where you can't do